Here we go. Second lecture video. We're going to hit up all them 20 vocabulary words. Okay, remember to study these words and definitions because they are used very closely on every unit's vocabulary test. So these are the special words of chemical bonding and molecule interaction. I do believe some of them will be repeats from a previous unit, but that's okay. Here we go. Cation. Oh wait, we've done that one before. Look it's a positive ion because it lost at least one electron. Aw, isn't it a pretty cation? It's the cutest ion ever. Okay, lose electron, cation because you're positive. Boom. Anion. The opposites, a negative ion because it gained at least one electron. Bingo. We're going to be combining anions and cations in chemical bonding. Ionic bonding specifically. Octet rule. We hit this up a little bit in our bell works, okay? All atoms want to have a full valence shell of electrons except for hydrogen and helium who want two, a duet. So everybody wants an octet to be like a noble gas, except for hydrogen and helium, which will handle a duet to be like a noble gas. So all the elements out there want to obey the octet rule. And that's what it is. Full valence shell. Get one. Period. End of story. Do what you got to do, fill up that shell. Even if it's a lose an electron from your next shell up, like in this picture with sodium in the reactive state. That one electron can say, see ya, and then it has 8 on the inside shell. And that's why it's stable. All right, so let's go. Chemical bond. Simply put, they are formed by joining of 2 or more atoms, resulting in stable electron configurations. There's got to be a reason for elements to form chemical bonds. Every party involved in the chemical bond achieves a stable electron configuration. It's the only reason why they will form a chemical bond. In reality, these 3 things are actual chemical bonds. Hydrogen bonding is not really a type, not a full bond. Okay, but we have to study it because it's the reason why water floats when it freezes. Okay, and it's got some special properties. Okay, so metallic bonds, ionic bonds, and covalent bonds are true bonds. Hydrogen bonds are actually a form of intermolecular force that's relatively strong. So that's why we put it on that chart. But here we go. Lewis diagram. Here's a picture of one. It's a picture, a diagram. It shows the bonding between atoms of a molecule or a compound. Lewis diagrams are useful because you can use them to show both ionic and covalent bonding versus, well, that's why we do it. So we did Lewis dots in the previous units to show the valence electrons. Now we're going to take those Lewis dot diagrams of the elements individually, combine them to make molecules and compounds. Simple enough. An ionic bond. What is it? Well, it's a complete transfer of electrons from a metal to a nonmetal, resulting in the formation of 2 ions. The metal loses an electron, becomes positively charged. The nonmetal gains the electron, becomes negatively charged. Opposite charges attract, creating a lower energy state situation and an ionic bond. So electrons given away, energy is lost, 2 ions get locked into place. Bada bing, bada bang, bada boom. You've got compounds instead of elements. Ionic charge balance is a really, really important thing to understand. If you have an element that lost 1 electron like lithium did here to become the lithium ion, it's only a +1 ion because it only had 1 to lose. When you try and combine it with an element that's gained 2 electrons, like oxygen, that oxygen has a 2 negative charge. So it's gained 2 electrons where lithium has only lost 1. So you need a second lithium to balance it out. So the ionic charge balances says that the charge of cations and anions must neutralize each other out into that, on that number line kind of math. So if you have a -2 oxygen ion, you have to have 2 +1 lithium ions to balance it out, resulting in the chemical formula of Li2, because there's 2 lithiums, 1O in this particular example. A polyatomic ion. We have a whole reference table of all the ones that you need to know. Here's some Lewis diagrams of some simple ones. Hydroxide, sulfate, ammonium. Basically what it is, it's 2 or more atoms that are bonded together covalently that will form an ion. Because as a molecule, it carries a charge. So it's a polyatomic ion. Ion meaning it's got a charge. Polyatomic, more than 1 atom. Simple enough, reference table E. A covalent bond. Here's a nice picture of a covalent bond. They're different in nature than ionic because they share their electrons between two nonmetals. Instead of completely transferring from a metal to a nonmetal, in a covalent bond, the two nonmetals, who both have high electronegativity values because they have high effective nuclear charges, want to hold on to their valence electrons. So they're willing to share it with a partner, but they're not going to let it go all the way because of that high effective nuclear charge, high electronegativity, high ionization energy. Nonmetals don't lose electrons. They share or gain them. Period. End of story. This is how it would look with Bohr diagrams. A molecule. Well, there's many billions and trillions out of there. We figured we'd pick 2 or 3 simple ones. Molecules are formed when 2 or more atoms bond together chemically. It's a bit of ambiguous argument. Is NaCl a molecule or a compound? Basically, it's both. Because when you form a bond chemically, you get a compound / molecule. Okay. Basically, what is put it like this is not all molecules are compounds, but all compounds are molecules. There's 7 molecules that are not technically compounds. It's the 7 diatomic elements. Moving forward. Yep, there we go. A compound, a molecule that contains at least 2 different elements. Different elements being the key term. If I have a molecule that contains 2 of the same element, it's not a compound, it's actually just an element, which is why I mentioned those diatomic 7. Here's some pictures of formations of 2 compounds. A cation and anion, sodium and chlorine, forming sodium chloride. A cation and a polyatomic anion, polyatomic, forming magnesium hydroxide. And notice, again, there's a little -1 here. You need 2 OH -1s to balance out your magnesium +2, which is why we came up with this notation that involves parentheses, okay? You don't need to know that yet, but you will by the end of the unit, that notation. Let's see what oxidation number is. Scary word. I hope it's not too bad. Oh, wait. It's the number assigned to an element or ion to represent the number of electrons that are gained or lost. So when I say, hey, what's the charge on this ion? And you say, hey, it's 2+ or +2. Well, that's the same as the oxidation number. It means the same dang thing. Why do we have to have so many terms that mean the same thing? Different terms meaning the same thing. Well, it's just how it's written. A polar molecule. These are not molecules that live at the north and south pole, but you can think of them as having north and south poles. It's an asymmetrical molecule, meaning it does not have a plane of symmetry. It has an uneven distribution of charge as a result. In this particular example, H2O has got this kind of bent shape. One side of the molecule's got oxygen, the other side's got 2 hydrogens. As a result, it has slightly negative and positive ends, depending on the electronegativity values for the elements. Oxygen's electronegativity is higher than hydrogen, so it pulls the electrons towards its side because it has a higher effective nuclear charge. It sucks all the electrons in that bond towards it more often, so we get ourselves a polar molecule. A nonpolar molecule, on the other hand, is one that is symmetrical. So there's planes of symmetry, and therefore you have an even distribution of charge around the particular molecule. Okay? These ones, when we cut them along a plane, it's the same on either side. You know? So it's a symmetrical sharing of the electrons. It's like a 2- or 3-way tug of war with evenly matched tuggers. Okay? That's just how it is. If you want to think about electronegativity as one element's strength for pull on electrons, like pulling on a tug of war, that's great. Polar and nonpolar molecules involve the tug of war being evenly matched or unevenly matched. Our polar covalent bond. These values are electronegativity values, 3s. Okay? A polar covalent bond shows you there's a difference in the electronegativities. Chlorine has a higher effective nuclear charge, so it pulls all the electrons towards it more often. A nonpolar one, which is going to be our next verge, no, we already did nonpolar. So that's a polar covalent bond. It's uneven sharing of electrons. Electronegativity is between, difference is between 0.5 and 1.3. We're going to practice that a bunch so we really get it. Nonpolar covalent bond. So I was talking about polar and nonpolar molecules at first. That's why I got tripped up. You might too, so be careful. A nonpolar covalent bond is when the electronegativity difference is 0. In this case, neither one of the atoms is able to pull stronger than the other. So it's a perfectly matched tug of war in the bond, and we see that there is no positive and negative side as a result. We already covered symmetry when I mentioned polar molecules, but here it is again. Symmetrical, even distribution of charge, making opposite sides of a molecule mirror images. So symmetricals are always going to be nonpolar. Even tug of war in all directions. The opposite is true for asymmetrical. I think we throw the same picture in there. It's an uneven tug of war. So we got this polar, right? Chlorine's going to win. Nitrogen's going to win. It pulls all the electrons towards it. Chlorine's going to win. Okay? So you end up with lopsided molecules that we call, as chemists, polar molecules. And polar molecules like to gang up together and interact with each other with intermolecular forces, which is our next word. There are a couple that you need to know. It's not a real bond. That's the big important part. Here's 2 molecules of hydrochloric acid. This is stomach acid in your tummy right now. These molecules line up head to tail because of the fact that they are polar. Right? If you've got a negative and positive side, well, opposites attract. So they're going to line up, tip to tail, tip to tail. It's just what molecules do during intermolecular forces. And the most important intermolecular force is hydrogen bonding. It's a very strong version of an intermolecular force. It is not an actual bond. It's just a very strong attraction between the oxygen, nitrogen, or fluorine of one molecule and the hydrogen in a different molecule. That nitrogen, oxygen, or fluorine has such a high effective nuclear charge that it pulls electrons from other molecules even in towards it to make it magnetic, if you will. So that's it for your vocab. There is no practice here, but be ready for your vocab quiz on Thursday. I'll have a small Google Classroom assignment for you to do. Thank you.